Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Bandits, published in 1983 by Sirius Software. The creators were Benny Ngo, Len Bertoni and Tony Ngo. This game was suggested by one of my YouTube members, so thank you very much for the suggestion. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel or sending me a super thanks. They are all always very much appreciated. First of all, let's look at the G64 disk image file in C64 debug GUI. This disk image doesn't seem to automatically start. It's got a little sys2061 at the beginning and it then loads Bandits. So there's a very small file and then there's a big file later on, and this big file takes quite some time. I'm going to skip ahead here because this really does take quite some time to load. Here in the C64 debug GUI drive debugging, all I can see is just the kernel loader doing its thing. When this game starts, we get this rather lovely attract sequence at the beginning. There's the rocket taking off from its launch pad and what looks like a bitmap screen, kind of wobbly, semi-smoothly scrolling up the screen. Now, this wobble tends to indicate to me that the entire bitmap data of the screen is being updated rather than the smooth scroll in the hardware Y smooth scroll that's available in the VIC chip. And that kind of makes sense because I think the bitmap screen is single buffered, and trying to double buffer a smooth hardware scrolled VIC bitmap scroll anyway is going to be quite time consuming, so why not just do a software wobble scroll. Moving up and down the debug VIC mode here with the crosshair up and down the screen, I can see where there's a couple of screen splits. So the screen down at the bottom and the screen up at the top seems to be using a different character set compared to the middle. The middle character set does seem to be alternating, and there does seem to be a double buffered screen as well, because the screen addresses were also alternating as the game was being rendered. It then loops back to this screen here. There's a rather nice little transition here. And then it goes into the game start. Let's turn the joystick on. That's always a good idea, isn't it, if I want to actually control the thing. So what strikes me here is that we've got this rather nice little horizontally scrolling kind of semi-parallax-ish, well, it is parallax, scrolling starfield there. But if we have a look at the debug view here, now remember in the C64 debug GUI, hardware sprites are surrounded by these red boxes. So we have hardware sprites down in the bottom and top borders. We have hardware sprites for what are currently they're not cherries, they're blueberries or something like that. On the right hand there, now they've turned into keys, now they're, I don't know, some kind of fruit anyway. There's 1, 2, 3, 4, 5 of them there. The player character ship is a hardware sprite. It is surrounded by a little red border there, a box. But the rest of the game graphics, the background, the enemies on the left that are parked there, the enemies that are flying around, importantly, are not sprites. Now, when the enemies seem to pick up one of those fruit on the right hand side that I think you're meant to be guarding, then that's still a hardware sprite, and that makes sense. If you're going to be rendering it as a hardware sprite on the right hand side, then it might as well be rendered as a hardware sprite when you're picking it up. That's fine, right? So this game was suggested to me because I think it was actually suggested twice, but one of my YouTube members suggested that maybe it would be a good follow-up game because a couple of my previous games were looking at bitmap rendering and software sprites, and they thought that this game used software sprites as well. Now, software sprites are when they look like sprites, but they're basically not using the hardware implementation of the sprites that's available in the VIC chip. So, well, I think we can safely say that this game is mostly using software sprites. It's also using hardware sprites for those game elements that we could see there. But the amount of software sprites in this game is actually quite impressive. I do like this attract mode sequence though. I think it really shows a lot of love and care and attention went into this game. It's good polish. Oh look, that mothership when it flies up the screen there, that's also not hardware sprites. That's really interesting. This game makes quite a good use of colour. I can see a little bit of colour clash there with the hardware sprites, software sprites, sorry, not hardware sprites, the software sprites. So when a green sprite was overlaying a white sprite, for example, I could see some colour clash. Now I'm just having a look at the disk image here with my updated C1541 debugging tool to try and see if there are any recoverable files. Sometimes, disk images, especially original disk images like this one is, they sometimes do contain hidden files or files that were partially deleted or left deleted by the developer or during the mastering process. So I'm using my added recover command, which basically looks through the disk image and it tries to find unreferenced block chains within the disk image that do not appear in the directory, and then it saves them out. The code for this updated version of C1541 is actually available on my GitHub repository. You can have a look at the code changes that were made from the original version of C1541 that I think was available in the Vice C64 emulator source code. So there's two chains here. Well, track 18 sector 0 is basically the directory block. Track 17 sector 1, there, that larger file. Let's have a quick look at that file in the hex editor. This is the directory block. That's the block allocation map at the beginning, and then another block for the directory. Not interesting. This file here, okay, so the start address seems to be a little bit suspect. So this file, it does contain quite a lot of blank data in terms of lots of zeros. There doesn't seem to be that much structure to the file, so I don't think it's really anything interesting. So I don't think we need to look into the disk image in too much detail now. So here we are in the title screen and just double checking, and yes, it's using a bitmap mode, especially for this screen here. It's still got bitmap there, highlighted in the C64 debug GUI. The green bitmap there indicates that the screen is in bitmap mode. But then when it goes here, it goes into the game mode and it's using the character display. We can see this because the charset debug window here is showing that when there are more software sprite enemies on the screen, then the number of dynamic characters in the charset increases. If I move the mouse pointer up and down here, we can see that the score panel up at the top and the bottom parts of the screen here uses a different character set. It contains text for the score and the lives and things like that. But this is basically a bitmap screen. And then we can see that the text box is now green, which indicates that this main game display area here is using a text-based screen. And we can see the screen and the charset information toggling between two screens and two charsets. This will need double checking, but it looks like the screen at 4000 in hex is using one charset, and then the screen at 4400 in hex or 4400 in hex is using the other charset. Let's go into my trusty Vice C64 and ICU64 tool now. So setting the device to 8, which is the drive, and then setting a ranged breakpoint from 0 to 1000 in hex. We're going to see if there's really any drive code running, and I really don't think there is, but we'll just really double check that. The Vice emulator combined with ICU64 is a really powerful combination for finding out what's going on. For reverse engineering, the C64 debug GUI has its use, but it has certain use cases, but the Vice and ICU64 combination tends to be a lot more usable for me and a lot more powerful in terms of what you can do, especially with the fully featured monitor. We can see here that as the game is loading its data, there was no breakpoint hit in the drive's lower memory, in its RAM, so we can pretty much safely say that there wasn't any drive code running. The only code running in the drive, of course, is in its ROM, and that wasn't part of the ranged breakpoint address space. Let's continue on with the load. So here we go, the load's finished. Warp mode was on. The game doesn't normally scroll the bitmap screen so quickly, of course. I do really like this attract mode though. Very nicely done. So the IOD000 command here will show us the IO state for the BIC chip, which is a D000, and it definitely confirms that it's using a standard multicolored bitmap screen, at least at this position on the raster position for this particular point in time where the monitor was stepped into. We can see that there is a screen, a bitmap screen at 20,000 in hex, the second half of the first bank, and then there is a duplicate of that screen at what would it be? It would be at A000, which is the second half of the third big bank at 8,000 in hex there. But once it does the transition and once it's gone into the game display, the bitmap screen is no longer updated. So that checkerboard effect is the transition from the title screen to the game. We can see here that the bitmap screen in this area of memory, if I edit it, let's put some squiggles in there. So I'm editing the bitmap screen, which is at 2000 in hex in the second half of the first big bank. Let's warp ahead until it gets back to the title screen attract mode. And when it displays this screen, yes, it's still displaying a text mode screen now because it's displaying the game mode screen, which uses a lot of these software sprites. Right, there we go. So it seems that the title screen here, well, it's displaying the screen in the third Vic bank. And oh, look, it's copied the screen in the third Vic bank from the backup of the screen in the first Vic bank. Okay. Well, it has two bitmap screens in memory then, one which is a backup bitmap screen and then one which is the displayed bitmap screen. And that's an interesting addition. Basically, the squiggles that I put in the backup screen in the first Vic bank were copied to the bitmap screen in the third Vic bank. Let's set up the graphics map view there in the top right hand corner of the screen to display the two text screens and also use the correct charset. So there we go, I'm showing one of the charsets at 5000 and then the other one at 5800 in hex. So it's definitely using two double buffered screens and two double buffered charsets. for the main game display, plus an extra charset for the top and bottom rows of the screen for the score panel. That's quite a lot of graphical data, but it doesn't need to have too many hardware sprites. So it's all kind of like a cost-benefit analysis, if you like. If you don't have a lot of hardware sprite definitions, then you can afford to have more character sets being available and visible in the same Vic bank, so that's perfectly fine. You'll notice here that if I switch between the two charsets, the correct charset that's visible for the correct screen bank makes sense. It looks correct in this debug view here. And then when I flip to the other charset, the other Vic screen bank data looks correct. It makes sense. So this really does tell us that this game is using two double buffered screens and two double buffered charsets, and each charset corresponds to each of the double buffered screens. That's quite a lot of data to update, isn't it? Let's use the other graphics map debug view now, and let's look at the charsets that are in memory in this second Vic bank, the Vic bank that starts at 4000 in hex. We can see immediately that the game is updating two of these charsets dynamically, depending on what's going on the screen. And we can see that the busier the screen, the more software sprites that are visible on the screen, the more charset data is computed. There are 3 enemies flying around, and there are a corresponding number of dynamic chars in the charset being created for those flying enemies. Let's see if we can find the code which updates the character set. We can look for the character set updates by doing a ranged watch point store between the two memory areas where the character set is stored, which is between 5000 in hex and 57FF, which is the ending address. Now we have some absolute stores here after information is loaded. This looks like, well, the accumulator is 0. It's doing a semi-unrolled loop, but with Y index values there. It looks like it's clear. Wow, it's clearing the whole character set. And Y goes from 0 to 0. It loops around all 256 values. So yes, it's basically clearing practically the whole character set before rendering into the character set. So if I put a breakpoint at the end of this loop here and then hop out of this routine, we'll be able to see that most of the character set of 5000 in hex has been cleared, and we'll see that in the charsets debug view once the code execution continues. So it's going to be that first character set there that we can see. There we go. Most of the characters in the character set have been cleared. Some are left behind, and those are the characters that's used for the main part of the game display, the curvy line on the right, the domes, the grass, if you like. I think those ones are kept. Now don't forget that the debug graphics map views show what's going on in the Commodore 64's memory. The main Vice view only shows the currently rendered frame that the Commodore 64 is displaying. It's at that particular point in time where it's stopped. So the graphics map debug views and for the characters, the character sets, the bitmap data, the sprites, they show a live version of what's in the C64's memory, whereas the Vice view only shows the previously rendered frame. So what we see in the Vice output view is going to be lagging behind what we see in the debug graphics views. That's going to be important later on, I think. It's important to understand how these debug graphics views actually work. They work in real time, whereas the Vice output is, you can think of it as lagging a frame behind. It's the last complete rendered frame. So we have this code here at D47 and around this area where it seems to be loading data, ORing it with what's in indirected register 0 page register 2 and 3, of course, the low and high byte, and then storing it back into the same address. If we have a look at M2 to 3, we can see that it represents in low byte, high byte order the memory address 50D0, which is basically roughly near the start of the character set, but not quite. It's basically skipping over the first few characters and then updating the dynamic character set information a little bit later on. This code here, if I step over it, well, I can see what looks like a bullet character starting to be created there. So this code here, it seems to be executed at least once per frame. Maybe that's because I've only got one enemy bullet on the screen. That would make sense, wouldn't it? So maybe this code is updating the enemy bullets. Let's see what else is updating this memory. Well, okay, so that's the routine that we were just looking at before. That's the second half of the same routine. I think that's the enemy bullets. Oh, look, this is interesting. This is a different routine which is doing a similar update, but it's doing a more complex update of more complex graphical data. F4, F5 is indirecting into what looks like the graphics data for the enemy frames. So the enemy graphics data is the source in F4, and F5, the indirected memory address load there, which is 6503 in hex. Seems to be loading that, ORing it with whatever's in the character set data, then storing it back into the character set data. And it seems to be doing that with maybe the next character set as well, and that's that indirected memory address of 12 and 13. So this load or store basically looks like the routine which is updating the enemy animation data into the dynamic character sets. And it's doing this quite a lot. So don't forget, I've got a watch point, a ranged watch point for any stores into the first dynamic character set for the screen, for the game display screen there. So yeah, that's interesting. So this routine seems to have some, they're not completely unrolled chunks, but it seems to be updating at least 2 different character sets all in one go. And then there's a similar kind of like chunk of code directly after it as well, but using slightly different indirected memory addresses for the store memory address and for the OR memory address there with the indirected code. So I'm pretty sure that this is, yeah, look, if I put a breakpoint there but remove the watch point for the memory store, and every time I execute the code, it's rendering one extra chunk of characters for each enemy. Okay, so yeah, this definitely looks like the enemy rendering code, which renders enemies into the dynamic character set. This is the memory watch store point triggering again for the character set clear. There's a corresponding clear for either the first or the second VIC screen bank there as well. I can see that those memory addresses 4428, 4450, 4478, 44A0, etc. They are all memory addresses in the VIC screen bank, either the first screen bank or the second screen bank within this second VIC bank, if you like. So this game definitely seems to be using quite an interesting way of using dynamic characters in the character set to have software sprites. Just updating my debug notes here. So the 9BA routine looks like the character set and character screen clear, for example. It then seems to render the bullets into the character screen and character set data. It then seems to update the character screen for the enemies, and then after it updates the character screen for the enemies, it updates the dynamic character set data for the enemies. And I've added that into the debug notes with the corresponding memory addresses for each of the routines, which seem to do what they're doing. The debug notes will of course be committed into source control, and you can access that file, this file rather, from my GitHub repository, and I will add a link to that in the video script description below. To test the hypothesis for where this graphics data is stored in memory for the animation frames, let's just update the pixel data in what I think are the animation data frames for the enemies, and then let's run the game a little bit and then see what happens on the screen. And yes, there we go. Straight away we can see that the enemy character set data for the software sprites has been successfully updated, so we know where the game is now copying this data from, and the format of that data is just basically what looks like a character based layout in memory, but of course the game does some copying around and stuff like that into the dynamic character set. So I've updated the debug notes to reflect that. So that's really interesting. It would be possible to extract the animation frames from these places in memory if you really wanted to for each of the enemy animation frames. Since we're back to the attract loop where this bitmap screen is kind of like wobble scrolling up the screen, yes, we can see that the vertical pixel level scroll is actually done in software, not using the hardware at all for this bitmap screen, which, as discussed previously when we were looking at this in C64 debug GUI, that's kind of like fine. It would be a little bit difficult to do a hardware pixel level scroll and having double buffered bitmap data. It would be kind of possible, I think, actually, with the amount of memory that's free, but it's a valid choice to do it in software with a single buffered bitmap screen as well. There's a little bit of cursive writing going on for the game over sequence, so I just wanted to see where this is. It's in the game display screen, so I'm pretty sure that the writing for game over occurs in the character set data there. Okay, yes, it looks like the characters have already been pre-populated into the screen, but it looks like the character set data is being updated after the characters in the screen have been put there. And yeah, that's basically updating the character set data afterwards. So again, the game over cursive writing that comes on the screen is updating into its dynamic character sets appropriately. We can get that back again just by dying a few times in the game screen. Let's zoom in just to really make it obvious. This is the graphics map view for the characters, the debug view rather. So when we die, yes, the cursive writing for game over goes into the appropriate dynamic character set data, and it's just built up that way, probably from I think some table driven rendering from memory somewhere. I expect it was painstakingly added to it like a table of pixels to draw. The debug bitmap view on the left is the bitmap with those squiggles that I added. The one on the right is the live view of the rendered Vic screen. And then when it does the transition, before it obliterates the rendered visible screen, it copies it into the low backup Vic bank, if you like. And that's why the squiggles disappeared, and then I had to redraw the squiggles into that debug view there. And that's because the live screen view which is currently not visible in the game demo mode, it's only really visible when you're looking at it from the title screen. It's currently showing the checkerboard pattern, and there we go. It's restored the visible title screen from that backup in lower memory. So this game attract sequence is actually quite involved. It does quite a lot of software updates. It does quite a lot of nice little transitions like that. And it also does the software vertical pixel level scrolling as well for the screen. So I'm also updating the debug notes to reflect this understanding. The large mothership during the game is of course rendered into the dynamic characters and character set data as well, just like the enemy software sprites are also updated into the dynamic character set data. So I think I've covered everything I wanted to cover in this game. There's quite a few little hidden gems in this game. It's quite pleasantly surprising to see such a detailed, polished game from such a long time ago. I think the developers really did a really good job in this game. So if you like watching these deep technical dive videos into Commodore 64 retro games, then please do consider liking or subscribing to this channel, and a super thanks or a membership of this channel is also very much appreciated, and you get your name scrolling up the screen in a thank you message. So thank you very much for watching. Take care, have a great day or evening or night wherever you are.